Okay, good day class. My name is Engineer Steven. I'll be continuing from my other class. This is the exquisite tutorial. So our major aim is to enlighten you on your 700 level stuff that you guys will be doing this semester. But today, like last class, I taught you guys electrostatics. This class I'll be teaching you Gauss Law. So Gauss Law, I'll be teaching you Gauss Law, the introduction. Gauss Law has to do with like a relationship that exists between electric charge when they are placed in an enclosed or imaginary surface, and the field. Like the last class I taught people electrostatics. We talked of the force that exists between charges, the interaction that exists between the charge and the force. But this time we'll be talking about Gauss Law. In Gauss Law, we relate the field and the charge, not the force and the charge. So that is the intro part. Then in Gauss Law, normally we use Coulomb's law in electrostatics, but for Gauss Law we'll be using electric force. Electric force talks of the number of electric lines, like the lines that pass through a metal surface or a conductor or anything. The lines that electric field line that pass through a metal surface or a conductor. Then the strength or the capacity of this electric force is dependent on the magnitude of the electric field lines that are passing of the electric field line that are passing through the metal plate or the conductor. Then the Gauss Law. The Gauss Law goes with this general formula. And normally our electric force is represented mathematically by this, or so our electric force is represented mathematically by this, that our electric force is equal to electric field intensity and the area of the plate or whatever you are considering. And normally our electric field intensity is equal to the electric force divided by the quantity of the charge. And our electric force from Coulomb's law normally, which we did earlier on, is equal to K Q1 Q2 all over R square. Q1 Q2, this our charge could be any of this charge up here, so it doesn't matter. Okay, divided by our Q, so that will be equals to so is either this charge we are talking about down here is any of these two charge. When the charge are similar, that is when we are considering this part. So it will be KQ all over R. No need of even writing this Q1 or Q2, so you should just understand it. So this is the formula for the electric field intensity. We can also induce it into this part. We induce it into this part to now be KQ over R times the area we are considering, depending on whatever area we are trying to deal with. Depending on whatever area we are trying to deal with. So now let's consider applying Gauss law to a point charge. So let's consider applying Gauss law to a point charge. Assuming this is a charge. First of all, if we want to apply Gauss law, we will think of an imaginary substance. Like this is a point charge now. We want to apply Gauss law to this point charge. We think of any substance, an imaginary enclosed substance that is similar to this charge, that I can use to determine like the Gauss law that I can use to solve the formula for this point charge. First of all, I haven't forgot, our Gauss law states that the electric force of a substance is equal to the quantity of the enclosed charge over the permittivity of free space. Just drop this one at the back of your mind, because I'll be using it to solve this point charge question. So assuming this is the point charge, you think of any substance that can somehow relate similar to this point charge you placed here. You now use it to determine the flux for the point charge. So I'll be taking a sphere, because if you look at the structure of a sphere, it's almost similar to that of an electron. The structure of a sphere is almost similar to that of an electron. And the distance between the sphere from this part, let's take it to be r. So this is the electron, the quantity of the charge rather. And this Gauss law is also equal to, like I said, our phi is also equal to EA cos theta if we are given an angle. So this thing is equal, from the Gauss law, our Q is equal to the quantity of the enclosed charge divided by the permittivity. Is also equal to, we can make it equal to EA normally from our normal aspect. From our normal aspect of any Gauss law, any electric flux formula. So from there, let's consider this shape we drew here. We want to determine the electric force, and we know that our flux is equal to EA. And I told you that our electric field intensity, also known as the electric field strength, is equal to KQ all over R squared. So in order for us to determine the flux, we'll be considering, I told you that we'll be considering the area of the enclosed imaginary substance. This substance, you are not seeing it now. You are just imagining that the substance is there, enclosing this stuff. So if we are considering this substance, the sphere as our point of view, the surface area of a sphere is equal to 4 pi r squared. Surface area of the sphere is equal to 4 pi r squared. So definitely this r squared will cancel this r squared. We will now be left with 4 pi kq. So from here, what we have to note is that the flux is dependent on the quantity of the charge, and the flux, from here we have to note that the flux is dependent on the quantity of the charge. And also it's also dependent on the electric field, or the electric field strength, or the electric field intensity. So before going to that part, there are some important points you are meant to know. For a system in equilibrium, when we say a system is in equilibrium, the electric field strength and like the electric field that exists in that system is equal, inside the system, is equal to 0. That is, the charge, if I say the electric field strength that exists in that substance is equal to 0, definitely for the electric field to be equal to 0, therefore the charge present in that substance also must be 0, or rather it must not be excessive. So for a metallic conductor to be in a state of being electrically equilibrium, the charge intimate or found inside the substance must be scarce, like it mustn't be excessive. The charge rather must be found outside the metal conductor or the substance, at the surface of the substance. and minus that, if the assuming this is a metallic substance, and this part is an empty space. Let's assume this is an empty space. This is an empty space. There's no charge found there, like a vacuum or something else. And there's presence of charge, electric charge outside. If we pass a field, like an electric field, towards this part, we'll find out that this part where there is charge, due to the presence of electric field, due to the presence of charge, the electric field will pass through there, thus expressing a flux at this part. But at this part where there is space, there won't be any flux, but rather the thing will just jump to the other part and come out from here. So that is that for my point. The notes or the special part you need to know. You must take note that electric force is dependent on the charge and is also dependent on the electric field intensity of a substance. So I'll be moving to our next point, how to determine the electric field of an infinite line of a charge. An infinite line of a charge I will call it a long wire. Determine the electric field of an infinite length of a charge. Before me determine the electric field of an infinite length of a charge, there are some certain things I want to explain. Assuming now this metal plate like this is placed in a electric field. This is an electric field line. The whole of this stuff, they are called flux. Then this is the field line. This the metal plate is standing like this. This is the flux. The flux is coming this way. The metal plate is standing like this. If you look at it, the surface of the plate is acting. If you look at it, the surface of the plate is acting perpendicular to the electric field line. Like this is the surface of the plate. Assuming this is my hand. Okay, let me use my hand as an explanation. This is my hand. Is standing like this. The flux are coming. The contact between these two bodies, like my marker and my hand, is expressing an angle. The angle is 90 degrees. The angle is 90 degrees. That 90 degree angle they express between each other is perpendicular in nature. So the metal plate and the electric field lines that are moving together, the surface of the plate is experiencing a perpendicular, like the angle between the surface for A. Let's assume this is A. For the metal plate A, the surface of the plate and the electric field line, if angle between them is 90 degrees. But if we look at our unit normal is acting parallel to the electric field line. That is why, so if you look at it at this point, our electric flux is equal to EA cos theta. Since I said the metal plate is acting perpendicular, if our theta here is equal to 90 degrees, if our theta is equal to 90 degrees, it will now be EA cos 90. And if you look at it very well, cos 90 is equal to 0. So the flux, the magnetic flux between the surface, the metal surface and the electric field line is 0. But if you look at that of the normal of the plate, like the vectorial normal of the plate, the electric field flux and the line, I said they are acting in line with each other, parallel to each other. So our cos theta here is equal to 0. At this point, we find that our cos 0 is equal to 1. We will now be left with just EA, our normal EA. But if you look at this plate placed downward, this plate that is placed at the bottom of this part, the electric field line and the surface of the plate, they are acting, this time the electric field line and the surface of the plate, they are acting parallel to each other, like they are following each other. So at that point, for the surface of the plate, the angle between them will be 0. So we'll be left with EA for the surface of the plate. But when it comes to our unit normal, it is now acting perpendicular. So our EA cos theta, now our cos will be 90 degrees. So for the other part, like I said, the unit normal is acting perpendicular. So EA cos 90. Cos 90 normal is equal to 0. So everything will be equal to 0. Our electric flux at that point will be 0. So what the point I'm trying to drive at here is that irrespective of a metal plate, a flat metal plate, when placed in a uniform electric field, depending on the position it is placed, its electric force varies. Like its electric force varies at the different position which it's placed. Like for this part, it's equal to 0, and for some part, it's equal to, like for this one now. This time the flux is inclined at an angle. The formula here will now be our flux normal is equal to EA cos theta. Since it's already inclined at an angle, there is no need. This is the way the relationship they exhibit, both that for the normal and that for the surface. They are both inclined at an angle theta. So that is the point I'm trying to drive out there. So let me go back to our normal discussion, what we were discussing, how to determine the electric field of an infinite line of a charge. So as I said, as usual, infinite line of a charge is like a wire, because a wire has electrons in the whole body of the surface of the metal conductor. Like the wire, a wire is a metal conductor. It could be copper or anything. So in order to determine the electric field, first of all we must determine the electric force, and in determining the electric force we will be using our Gauss law. So this substance, we will not think of an imaginary substance that can enclose this metal, or a substance that is somehow similar to this metal wire. The substance that will come to your mind is a cylinder. First of all, if we place a cylinder here, let's assume this is a cylinder. You find out that the cylinder will enclose this stuff. Sorry about my diagram, I might not be good in drawing that way, but it's the best I can do. Then at a particular part of it, take that part to be the area, a change in area. In this metallic conductor, the electric force they act at both ends. So we want to determine first of all the electric field, but in determining the electric field we take note of the electric force. So from Gauss law, as I earlier taught, this is the formula we use in solving this kind of stuff. So this time we'll be considering a cylinder, and since we are taking the area of just a particular segment of the cylinder, that particular segment is the surface area of the cylinder. And from our normal perspective of volume and surface area from plane shape, we know that the surface area of a cylinder is 2 pi r. So our E, this is our major point of view, because we are looking for we have gotten the electric flux. This electric flux for solving any law at all, like any substance, any metal conductor, any substance we are using from Gauss law. This is our standard law. But what we want to determine is the electric field. So we place in mind that our surface area of a cylindrical substance is equal to 2 pi RL. This is the standard formula for solving the surface area of any substance. So if we apply the surface area here, it will now be 2 pi rho L is equal to Q enclosed for the enclosed conductor which has charge in it, divided by the permittivity. So from here, we are to determine the electric field of the infinite wire. Our E will now be equal to the Q enclosed, the quantity of charge, over 2 pi rho L permittivity. 2 pi, this is the standard formula for solving the electric field of an infinite line of a charge, that is an electric wire, considering the area of the cylinder. But before doing this part, there are some certain standard formulas we use in determining the surface density, the line density, and the volume density of a substance. Like the line density of a substance, lambda, that is the charge per unit length, it is equal to the quantity of the charge over the length. This one you are just expected to have it at the back of your mind. Then the surface, this is the line density, this is the surface density. The line density, the area density is equal to the quantity of charge divided by the area. Then our volume density, our volume density is equal to the quantity of the charge divided by the volume. So this standard formula, you need to be at the back of your head anytime you are solving this stuff. So since I said our charge per unit length is equal to Q over L, if we apply that to this part of the equation, this is our Q, this is our L. So anywhere I see QL, I'll put lambda, which is our charge per unit length, or the line density. So if I introduce it here, it will now be Q over L, making it lambda. We'll be left with E over 2 pi rho permittivity naught. So this is standard formula for solving the electric field intensity, or the electric field of an infinite charge. But I can also do something. Since we are seeing the permittivity of free space, assuming we're given the permittivity of a medium or any other substance, we can use our relative permittivity. Our relative permittivity relates permittivity of free space and any medium together. So I can say our relative permittivity is equal to the permittivity of any material or medium divided by the permittivity of free space. So since, assuming we're told to find the permittivity of any material at all, our E is equal to lambda over, this time we're not dealing with that of free space, 2 pi rho over the permittivity of any medium at all. We can replace it with, this is the permittivity of the medium. It can be equal to E is equal to E rho times E naught, where this one is the permittivity, relative permittivity, and this one is the permittivity of free space. Assuming we were given the permittivity, the relative permittivity and the permittivity of free space, but you're not giving just the relative permittivity, then you will now have in mind that they are telling you to find the electric field of an infinite wire when the material is found in a medium, not in just an ordinary vacuum. So our formula can also now be lambda over 2 pi rho. Replacing this one with this one, it will now be E rho times impermittivity. So that is the formula for solving this one. So I'll be moving to the field of an infinite plane sheet, of an infinite plane sheet of charge. So for the field of to determine the electric field of an infinite plane sheet of charge, assuming we have a plane sheet. This plane sheet now is a non-conductive substance. It can be a paper, like any sheet at all, provided that there is an electric charge found in it. So let's assume this is the plane sheet. First of all, you are going to place the plane sheet in such a way that you can easily determine, in such a way that you can easily determine the electric field strength of the substance. If I'm done with this, I believe you understand what I'm trying to say. So in this plane sheet now, in order for me to find a particular substance, like an imaginary substance that I will relate with, like when I did the one for that charge, or just a unit charge, I used a sphere. When I did the one for the line or the wire, I used a cylinder. This time I'll be using a cylinder, but this cylinder is just cutting through a particular segment of this non-conducting plate sheet carrying electron around it, to just cut through a part from it. So the cylinder is just cutting through a part of it, and normal, as I said, electric field strength will be flowing through this part and this part. So the normal formula for our electric force, our standard Gauss Law formula, is our electric force is equal to EA and is equal to Q enclosed when the charge is enclosed in an enclosed imaginary surface, divided by the permittivity. So before doing this aspect, I can also write this formula as this way, because if we integrate, like from our normal mathematics now, we know that if we integrate a differential of any formula, it will give us back that normal formula. So if I differentiate the area, it will give me our normal area that we had before. So it's the same thing, I didn't do anything special there. Is equal to Q enclosed. So for this substance, we are not going to be determining the area for this one. We are just going to be considering the two parts where it's affecting when it comes to a plane sheet of metallic conductor. So from there, if we differentiate the area, it will now give us EA is equal to Q enclosed over the permittivity. But since we are considering the area of this part and that of the other part, that is this part and that of the other part, we'll be considering twice of the area, not just a single of the area. We'll be considering twice of the area, not just a single of the area. Remember that all this is equal to our electric flux as we did as usual. So since we are looking for the electric field strength, our E, we will not make E the subject of the formula here. It will not be Q over 2AE. We'll be left with, if we make E the subject of the formula, these two guys will come down here. So we'll be left with this as our normal standard formula for solving it. So like I told you before, our quantity of the charge, our surface density is equal to Q all over the area. Standard formula for surface density of the surface of this metallic sheet non-conducting surface, but carrying charge around it. So if we are now introducing our surface density here, and our surface density is equal to Q, whether big Q or small q, Q over A, it will now be sigma all over 2 permittivity. So this is standard derivation for determining the electric field intensity of an infinite plane of infinite plane sheet of charge, and that for the one of the electric infinite line of a charge, like the long wire we did just now. The other aspect of my of my lecture I'll be explaining will be the calculation aspect, where I'll be solving some questions, and at the end of the class I will leave some questions for you guys, so you guys can drop those questions on the comment box that I will solve it later for you.